Assalamualaikum warahmatullahi wabarakatuh and a very good day. This video presents you the group project revolving waste management of pulp and paper production for environmental engineering subject from Group 1 Class C EEH 2207H. Group 1 comprises of 6 team members, which are Muhammad Izzat Shafiq, Imran Naim, Nur Suhaila Natasha, Izlisha Izwa, Fatin Rohaina, and Ainin Sophia. The presentation will be covering on the process description of pulp and paper, waste identification, acts and regulation, selection of waste pollution handling strategies and method, mass balance, conceptual design of each equipment, summary of IETS, process flow diagram, and conclusion.
There are two types of processes that involve in paper packaging production, which are pulping process and paper process. Figure 1 shows the process flow diagram for pulping process, while Figure 2 shows the process flow diagram for paper process. In the pulping process, pulp can be done mechanically and chemically. There are several equipment that were used in the pulping process. The process starts with the wood logs as a feedstock were prepared into wood debugging using debugging drums. Then, the debugged wood was entered into chipper to transform into wood chips. Next, the wood chips undergo into digester, where the wood chips were cooked in the digester at temperature 200 degrees Celsius and pressure 9.6 atm. The wood chips were dissolved with caustic solutions called white liquor. White liquor is a mixture of water, sodium hydroxide, and sodium sulfide. After being dissolved, the remaining of white liquor will be turned into black liquor. The resulted product that were removed from the digester were called as a pulp. Next, the pulp was cleaned and washed using washer to remove some chemicals in black liquor and subsequently was entered into bleaching tower for bleaching process. In the bleaching process, the washed pulp was bleached using chlorine dioxide to give a white cleaner color. The bleached pulp was refined and stored into a bleached pulp storage tank. The remaining bleaching agents will mix with black liquor and to be sent to the wastewater treatment system. The bleached pulp will be undergoing paper manufacture for paper making process. Next, for the paper process, there are 3 main sections that were involved, which are forming section, press section, and dry section. The process starts from the bleached pulp that come from the pulp process will pump into a box using wire belt. The wire belt will remove the water content in the pulp and leave the fiber to form a paper. This process is a continuously process where the paper continue to be pressed, heated, and dried using a continuous roll known as a web to get a piece of paper. After finishing, the paper was stored and shipped as a final product. So that's all for the process description for the production of paper packaging.
The waste produced from the company could be divided into 3 categories, which are liquid waste, solid waste, and gas waste. The liquid waste is where 20 meter cube per ton of effluent is being discharged. These flow rates contains 15 kg per ton of total suspended solid, 5 to 20 kg per ton of BOD, and 20 to 40 kg per ton of COD. As for solid waste, the waste were sourced from debarking drum, chip screening, wood yard, slash deck, pulp denotting, recovery boiler, and also causticizing. The pollutants produced from these sources are bark, pins and fines, wood waste, sawdust, knots, sodium salts, dregs, and drip. The estimated amount of solid waste is shown in the slide with the unit of kg per ton. Finally, the gas waste was sourced from recovery boiler, lime kiln, bark boiler, and digesters. The pollutants produced were sulfur gases, oxides of nitrogen, and also particulates with the estimated amount shown in the slide.
Did you know that improper waste disposal can harm the environment? That's why Malaysia has strict regulation for managing scheduled waste under the Environmental Quality Scheduled Waste Regulations 2005. Scheduled waste, or SW, is classified into 5 categories based on its compositions and potential hazards. SW1 includes metal-based waste like lead, mercury, and cadmium, which can be toxic if not handled properly. SW2 covers inorganic waste such as acidic or alkaline residue that may contain metal or organic compounds. SW3 includes organic waste like solvent, contaminated oils, and sludge from chemical process. SW4 is a broad category covering various hazardous industry by-products and residue. SW5 includes special hazardous waste such as explosive or reactive materials that require strict handling.
Okay, I'll be talking about waste pollution prevention strategies in the paper industry with a focus on solid waste. But before that, let's take a step back and talk about waste management in general. In the paper industry, waste can be categorized into three types: solid, liquid, and gaseous waste. Each of these require different handling method to reduce pollution and minimize environmental harm. Without proper management, waste from the industry can contribute to land pollution, water contamination, and air pollution due to greenhouse gas emissions. That is why effective prevention strategies are crucial in making the industry more sustainable. Today, I'll be focusing on solid waste and 4 key strategies used to manage it. The first strategy is thermal processes, where heat is used to treat and reduce waste. This includes incineration and combustion, which burn waste to reduce its volume while recovering energy. Pyrolysis is another method that heats waste without oxygen, producing useful byproducts like bio-oil and gas. Lastly is wet oxidation, treats high moisture waste using heat and pressure, breaking it down into biodegradable products. Next, we have composting, where microorganisms break down organic waste into nutrient-rich soil conditioner. It is a natural and eco-friendly way to recycle paper sludge, but it requires time and space to manage properly. Another method is land application, where treated paper mill sludge is used to improve soil quality. Since it contains calcium carbonate, it helps neutralize acidic soil. Lastly is anaerobic digestion, break down organic waste without oxygen, producing biogas that can be used as a renewable energy. Since paper mill sludge has inorganic material, it often needs to be mixed with other organic waste to work efficiently.
The pulp and paper industry generates significant liquid waste, requiring an industrial effluent treatment system (IETS) with 3 main stages: primary, secondary, and tertiary treatment. In primary treatment, physical and chemical method remove large particles and suspended solid. Screening eliminates debris, while the equalization tank stabilizes fluid. Coagulation and flocculation aggregate smaller particles for easier removal, and the primary clarifiers settle out solid. Secondary treatment uses biological process to break down organic pollutant in the air. In the aeration tank, microorganisms decompose waste with oxygen support. The activated sludge process forms sludge floc to capture contaminant, while the secondary clarifiers separate treated water from sludge. Tertiary treatment ensures the final effluent meet environmental standard. Filtration removes fine particles. Meanwhile, advanced oxidation breaks down pollutant, and disinfection via chlorination or UV eliminate pathogen. In addition to this treatment, industry can adopt supplementary waste prevention strategies to enhance sustainability. Water recycling and reuse help reduce freshwater consumption by treating wastewater for reintegration into production process. Chemical recovery systems such as black liquor recovery allow for the reuse of chemicals, minimizing hazardous waste discharge. Furthermore, process optimization can significantly lower water and chemical consumption through improved operational efficiency. By implementing this prevention strategy, the pulp and paper industry can significantly reduce wastewater pollution, comply with environmental regulation, and contribute to sustainable manufacturing practice. The pulp and paper industry emit various gaseous pollutants, including volatile sulfur compound, nitrogen oxide, and sulfur dioxide, which contribute to air pollution and environmental harm. To mitigate these emissions, several waste pollution prevention strategies and treatment methods are implemented. One effective approach is physicochemical treatment, which includes adsorption using activated carbon filter to trap pollutant, adsorption using scrubber to neutralize acidic gases like sulfur dioxide, and thermal or catalytic oxidation to break down harmful compounds into less toxic form. Additionally, condensation technique can recover high concentration VOC, reducing emission from mechanical pulping and wood processing. Another sustainable method is biological treatment, which uses biofilter and bioscrubber to remove pollutants through microbioactivity. In this process, gaseous contaminants are transferred to a liquid phase and then degraded by microorganisms, converting harmful compounds into harmless byproducts like carbon dioxide and water. To ensure compliance with environmental regulation, industries adopt best available technique BAT as outlined in the Environmental Quality Clean Air Regulation 2014. This technique focuses on optimizing industrial processes, improving emission control system, and using cleaner production technology to minimize air pollution. By integrating these strategies, the pulp and paper industry can significantly reduce gaseous emission, improve air quality, and support sustainable environmental practices.
The industrial effluent treatment system is used to treat wastewater from industrial activities before it is discharged into the environment. The treatment process follows several stages: preliminary, primary, secondary, and tertiary treatment. This step ensure that the wastewater meets the Industrial Effluent Regulation 2009 before being released into water bodies. Today, I will be focusing on the preliminary stage, specifically fine screening. So fine screening is the first step in the wastewater treatment and play a crucial role in removing solid particles from the water before it moves on the next stage. These solid particles may include organic matter, suspended solid, and debris that can damage equipment like pumps and pipeline. By removing this material early, fine screening helps improve system efficiency, reduce maintenance costs, and extend the lifespan of treatment equipment. The screen opening typically range from 1.5 to 6 mm, and the process is effective in removing 35% of suspended solid and BOD from the wastewater. So with the concentration of BOD is 5,000 mg per liter and suspended solid is 15,000 mg per liter, fine screening is able to screen out to BOD 3,250 mg per liter and TSS is 9,750 mg per liter.
So, the primary function of the equalization tank include a flow regulation which help to balance the fluctuation in a wastewater flow. Next is a pollutant balancing which stabilize the variation in a contaminant and concentrations. For the assumption of this system, the equalization tank does not provide any treatment, means it purely for a flow balancing and homogenizations. Second, it operates as a completely mixed system which stabilize the pollutant variation without removing or altering them. And lastly, there's no aeration or chemical are added to ensure that the wastewater remain unchanged in the composition. Now let's take a look at the block diagram. So as we can see, the flow rate entering and exiting the tank remain the same at 4011.46 meter cube per day. And for the parameters such as pH, BOD, COD, and TSS remain consistent from the inlet to outlet, providing that this tank help to maintain the uniformity in the wastewater before it moves to further treatment stages.
The coagulation tank functions to destabilize suspended particles by neutralizing their charges using coagulants like alum sulfate in the tank. The mixing process encourages small particles to form small flocks or microflocks. As for flocculation tank, it is where the small flocks turn into a larger and denser flock, encouraged by slow mixing. The assumption of mass balance of these two equipment are according to literature review. Firstly, the dosage of alum sulfate used is 60 microgram per liter. The BOD removal efficiency is 55%. The COD removal efficiency is 65% and TSS efficiency removal is 83%. The pH is reduced to 6 after 20 microgram per liter of lime is added. The flow rate of coagulation and flocculation tank is shown in the slide.
So I will explore the mass balance of primary clarifier in wastewater treatment. The primary clarifier plays a crucial role in removing suspended solids and organic matter from wastewater. This process relies on a gravity to settle out particles, improving water quality before the further treatment. So we assume a sedimentation efficiency of 91%, meaning that a portion of total suspended solid TSS is effective removed. So now let's look at the mass balance. The influent flow rate Q in is around 4011 cubic meters per day with an initial TSS concentration of 1657.5 mg per L. After dissemination, the influent flow, the Q out remains the same, but the TSS concentration is reduced to 149.17 mg per L. So this shows that the effective of primary sedimentation in removing solids and make sure better wastewater treatment efficiency.
Next, the section for mass balance for aeration tank. There are three functions for the aeration tank. First, this tank is for oxygenation process for the microorganisms. Second, this tank is for biological degradation between microorganism and wastewater as a food supply. And third, this tank is a mixing between the wastewater and sludge treatment. There are two assumptions that can be made to do a mass balance for aeration tank. First, the percentage of biological oxygen demand removal is around 95.88%. The percentage removal for chemical oxygen demand COD is around 95.711%. From the assumption, we can do a mass balance calculation for aeration tank. Based on the figure below, we can see that the BOD influent for the aeration tank is 1462.5 mg per liter, followed by COD influent is around 7000 mg per liter, and the pH influent is about 6. After do a mass balance calculation, the BOD effluent that can be obtained is 60.26 mg per liter, followed by COD effluent is 300.3 mg per liter, and the pH effluent will remain as a 6. The influent flow rate and the effluent flow rate did not affect the mass balance calculation. So that's all for the mass balance aeration tank.
The secondary clarifier plays a crucial role in separating treated water from sludge after biological treatment, ensuring that the effluent meets environmental standards before discharge. The mass balance calculation for the clarifier are based on several key assumptions. It is assumed that the system operates under steady-state conditions with a constant flow rate throughout the process. Additionally, the removal efficiency for biological oxygen demand (BOD), chemical oxygen demand (COD), and total suspended solid (TSS) is 97.6%, 91.6%, and 95% respectively. Based on this assumption, the calculated BOD outflow is 1.45 mg per liter, COD outflow is 25.23 mg per liter, and TSS outflow is 7.6 mg per liter with a sludge volume of 0.359 m3 per day. This result confirms that the secondary clarifier effectively reduces organic pollutant, improving water quality and ensuring compliance with environmental regulation before final discharge.
Okay, fine screening is the first unit operation in wastewater treatment. To design an efficient fine screen, one important parameter to consider is head loss, which represents the energy loss as water flows through the screen. The head loss through a fine screen is calculated using a specific formula where HL is head loss through the screen, G is acceleration due to gravity 9.81, CD is coefficient of discharge, A is effective open area of submerged screen, and Q is wastewater flow rate. To simplify the calculation, we use the following assumption. Typical fine screen opening size is 6 mm, coefficient of discharge for a clean screen is 0.6, effective open area of submerged screen is 0.46 m3. So based on this value, the head loss obtained is 1.4424 times 3 power of negative 3 meter.
So for the conceptual design of an equalization tank, starting with the assumptions, the design factor of this tank is 2, ensuring a safety margin for a variation in flow and load. And additionally, the normal detention time for a standard full plant is assumed to be 3 hours, which is TD equals to 3 hours to ensure the adequate retentions before further treatment. Now we look at the design parameter. So the effluent flow rate has been calculated and it leading to a minimum tank volume of 1002.865 m3. So the tank is designed with a diameter of 9.5 meters and a height of 40 meters, and each shape is cylindrical, which is a common design for efficient mixing and space utilizations. And finally, the actual detention time for the design is 5.937 hours, meaning that the wastewater will stay in a tank for nearly 6 hours before moving to the next stages.
The design of coagulation tank utilizes the assumption of detention time of 3 minutes with safety factor of 2 and shape of tank to be square. The resulting design effluent flow rate is 8,022.92 m3 per day with minimum volume of tank of 16.7141 m3. As for the design of flocculation tank, the detention time is set at 20 minutes with the safety factor of 2. The suggested tank shape is square, similarly to the coagulation tank. The design effluent flow rate turned out to be 8,022.92 m3 per day with the minimum volume of tank to be 111.4394 m3.
I will explain the conceptual design of a primary clarifier in a wastewater treatment. Before we dive into the design, let's look at the key assumptions. So the overflow rate is 40 cubic meters per square meter per day. The clarifier depth is around 3 meters. A peak factor of 2 is considered to handle variations in flow. Now, let's go through the design parameters. The design influent flow rate is around 8,000 cubic meters per day. The minimum tank volume is around 39.95 cubic meters. The detention times is around 2.56 hours to make sure that enough time for solids to settle. The surface area of the clarifier is 200.6 square meters with a diameter of 15.23 meters of efficient sedimentation. So this concept design makes sure that effective suspended solid removed before the further treatment.
Moving on to the conceptual design for aeration tank. There are 4 assumptions that can be made to design an aeration tank. First assumption is the yield coefficient is 0.5 kg per kilogram. The second assumption is the sludge age is 10 days. The third assumption is decay coefficient is 0.05 per day. And the last assumption is biomass concentration or MLSS is around 3000 mg per liter. In this conceptual design for aeration tank, we are considered 3 parameters to design an aeration tank. First parameter is design effluent flow rate. The second parameter is minimum volume of tank, and the third parameter is detention time. So, based on the calculation, the design effluent flow rate that we'll obtain is 8,022.92 meter cube per day. The minimum volume of tank that we calculated is about 6,249.59 meter cube, and the detention time that we obtain is about 1.56 days. So that's all for the conceptual design for the aeration tank.
The secondary clarifier is designed to ensure effective sludge settling and water clarification, allowing for the separation of treated effluent from biological solid. The design follows key hydraulic and operational parameters to optimize performance and ensure compliance with environmental regulations. The clarifier operates at under steady state condition, maintaining a wastewater flow rate of 4,011.46 meter cube per day. It is designed to remove at least 95% of suspended solid, ensuring high treatment efficiency. The assumptions taken to design this tank are 33 meter per day of the overflow rate, 2 to 3 hours of retention time. Then the shape chosen for the secondary clarifier is in circulation with a depth ranging from 2.5 to 3 meter. Therefore, the result obtained for the design effluent overflow rate are 8,022.202 meter cube per day with an area of 243.0970 meters square and diameter of 17.5932 meters to accommodate the flow and sludge retention need. The total tank volume is 1,215.485 meter cube and the hydraulic retention time is 3.636 hours, allowing sufficient time for sludge settling. This conceptual design ensures optimal pollutant removal, enhanced sludge separation efficiency, and supports sustainable wastewater treatment operation while maintaining compliance with environmental discharge standards.
So this is the process flow diagram (PFD) of wastewater treatment. So the process begins with an untreated wastewater entering the system where it first undergoes screening to remove the largest debris, and the water then flow into the equalization tank, which help to regulate the flow and pollutant the concentration before moving to the coagulation and flocculation units. In here, the alum and polymer are added to promote the particle aggregations, making it easier to remove the suspended solid. Next, the mixture will enter the sedimentation tank, where the heavier particle will settle down at the bottom and forming sludge. The clarifier water will proceed to the secondary clarifier and then pass through a carbon filter before being safely discharged into the inland water. Meanwhile, the sludge is directed to aerated lagoons and sludge tank holder, where the biological treatment occurs, and the remaining sludge is processed using a press filter, producing a sludge cake as a final byproduct.
To wrap things up, let's go over the key takeaways. The pulp and paper industry plays a big role in the economy, but it also generates solid, liquid and gaseous waste, which can have serious environmental impact. That's why proper waste management is crucial. This study has explored different waste types, their effect and the regulation in place, such as Environmental Quality Act, EQA 1974, Industrial Effluent Regulation, IER 2009, and the Clean Air Regulation 2014, to ensure industry follow proper environmental standards. To minimize pollution, various waste treatment strategies have been discussed, including mass balance analysis, treatment system design, and resource recovery. By integrating primary, secondary, and tertiary treatments, industry can effectively manage wastewater, reduce emission, and handle solid waste more efficiently. Using the best available technique, BAT further enhance sustainability and helps reduce the industry ecological footprints. Moving forward, continuous improvement in waste treatment technology, stricter regulatory enforcement, and greater commitment to sustainability will push the industry towards greener and more responsible operation. Research and innovation in waste treatment and environmental engineering will also be the key in ensuring cleaner and more sustainable future. That's all from us. Thank you.